Good morning, everyone. I do want to take 45 minutes here. Going to have some prepared remarks, and then we'll leave time, hopefully, for 15 minutes or so of questions at the end. But I'm always love coming out here. I'm really excited to talk to this group, where there are a lot of people I understand who are either data science practitioners or people who manage data scientists. So this should all, I hope, feel relatively familiar. But I do think it's worth kind of talking about maybe how the outside world sees data science and some of the hype that occurs around that. So you can see statistics like this. This is a data point that IBM has published periodically. So 90% of the world's data was created in the past 2 years. It's obviously a very literal-minded interpretation of what data is. It's bytes and stuff. It's not like actually like useful information. I sure as hell hope that 90% of the world's useful knowledge is not only 2 years old. But I do like to contrast that kind of hype against things like this, for example, against the fact that Donald Trump won the presidency 2 years ago. We can talk about how likely or unlikely that was. I think not as unlikely as people think, but nonetheless, I kind of work, among other things, in the realm of prediction, and I'm not sure you could really say that society has gotten a lot better at prediction. Where you think about politics, you think about natural disasters, you think about financial crises, you think about flu epidemics, think about all these things. And my kind of book is about how, for the most part, mankind and womankind has been trying to predict civilizations, predict events for many, many years, and maybe has not gotten a whole ton better at it. You have to be a bit careful because, by definition, things that are newsworthy are things that are kind of unexpected. That's one thing I learned kind of working for a website that we cover the news, that the routine is not always very interesting. But still, I think there's a bit of a clash between the idea that, hey, we have better information, more data, we're getting smarter all the time, and yet the world still remains often quite unpredictable to us. In a slightly less kind of abstract sense, there is also a problem which is called the replication crisis, which occurs in medicine and psychology and many other academic disciplines, where a very high percentage of findings that are deemed to have a significantly positive result in medical journals, psychological journals, economics journals cannot be replicated. So you conduct the same experiment, you don't get the same result, or you tweak something very minor, not able to replicate it. The data might not be there, it might be proprietary data. This is problematic too. It suggests that there are problems I'll describe in a moment here, where when you get bigger data sets, then you have much more capacity to search through that data set for plausible hypotheses. There are a lot of false positives here, in other words. But like this is something that people are just becoming more aware of right now. I think it's kind of good that people are becoming more attuned to the fact that actually there are new sets of problems that we have now that we are in the era of big data. But thinking through those is, I hope, one of the themes of my book and of the presentation this morning. So what are the problems that you have when you get more data? I guess you would think that in general, when you have more data, well, that has to be better. But there are different types of challenges that can present. One of which is simply that when you have more data, there is more room for alternative interpretations of the same evidence. So one of the things I cover, of course, is elections and polling. This is a chart showing every national poll in 2016 between Hillary Clinton, who is the blue dots, and Donald Trump, who is the red dots. And so you have this kind of whole mess of information. And the question is, how do you connect these dots together to understand how national polls are changing over time? One answer is that it's actually not very obvious how much you're supposed to connect the dots. Here's the way that 538 does it, for example. Picking the amount of smoothing is not a trivial problem, for example, but you see that basically things are up and down a little bit. In the end, Clinton was ahead in the popular vote, and she did win the popular vote, which gets you, I think, a bag of chips or something. But the point is, even this interpretation, there are different degrees of complexity. And you get to the Electoral College, the whole challenge with the Electoral College is that you have 50 different states that are voting, but they're all partly correlated. So there are different models, as you can kind of see here. Believe it or not, I got in a lot of crap before the election for giving Trump too much of a chance. But you see that there are all types of interpretations of the same evidence that have very different odds for Trump. So anywhere from roughly a 1 in 3 or a 1 in 4 chance where we had Trump and where the Trump campaign itself had their candidate, from what we understand, down to a 1 in 100 chance from the Princeton model, 1 in 50 from the Huffington Post model. these are really different forecasts, and usually when you see really different forecasts, it's because you have different information that you're trading off. In this case, all these models, frankly including the Trump campaign, because they didn't do very much of their own polling, are all looking at the same publicly available information and interpreting it in very different ways. And so the notion that we are reaching consensus in data science and solving all these problems, I mean, we're still, I think, not in the dark ages anymore. We're not in the dark ages, but we are like in an age of discovery, an early stage where the science is not settled. Because believe me, election forecasting, although an interesting challenge, is not nearly as complex a problem as some of the things that you guys are dealing with every day. So the fact that relatively simple applications, you can have so much disagreement, is indicative, I think, of how far there is to go in some ways. The next problem, which is sort of related to this, is that as you get more data in your universe, then there are more plausible hypotheses to evaluate, and the signal-to-noise ratio actually gets worse. So if you're in an environment where you have, for example, 5 data sets, what we're interested in when we study data, I know you understand, is we're really interested in relationships. How does A affect B, or how is A affected by B? Data itself, I mean, it's not like the numbers for numbers' sake. It's about understanding relationships, having some notion of correlation, and ultimately of causality for how a particular system works, what drives what. So if you have 5 data points, or 5, rather, columns in your spreadsheet, there are 10 relationships that you can test. If you expand to 10 types of data, you have 45 now that you can test. You see the exponential, I think it's actually geometrical increase, but you see what happens in an environment now where economic data, the Federal Reserve now publishes 508,000 economic statistics in real time. So if you want to correlate potato production in Idaho with GDP in Azerbaijan or something, you can do that. And so there are 258 billion possible combinations of two-way relationships that you can test. So what's the problem here? Well, there's a saying, I live in New York. There's a saying that if you're 1 in a million in New York, there are 700 people just like you. That's the problem with data sets this large, where you can find lots of 1 in a million relationships, but they're going to be, when you have essentially infinite ability to parse through a data set, you have infinite ability to find false positives, in essence, when data sets are this large. And this is a problem that's behind the replication crisis, behind the fact that overfitting and p-hacking are big problems, which just are different terms for describing when you're overly molding a data set to past data and not thinking about will it actually predict well and describe the fundamental features of the system very well. These are challenges that people are now encountering in the real world that they weren't thinking as much about 3 years ago or 5 years ago. I'll give you one more kind of slightly more abstract example to give you the problem where the signal-to-noise ratio is low in environments of big data. So this is supposed to represent a system in which there are relatively few actual signals, as I would call them. So the 10 circles in right are signals. They might be significant relationships in your data set. They might be, for example, in medicine. I gave a talk to some medical practitioners last week. They could be women, for example, who have a diagnosis for a certain type of rare cancer, for example. So you have a few true positives and lots of negative results. But you say, okay, look, I'm trying to find these positives, and I have some filter that filters out 80% of the noisy data points and correctly detects 80% of the signals. And so that seems pretty good. You've made a lot of progress from this kind of very imbalanced ratio before. But still, if you kind of recombine this data, you're still in an environment after that first screen where you have more false positives than true positives. I know it sounds like really abstract, but like I said, this is kind of the idea behind the replication crisis, that like there are only so many truly interesting and meaningful relationships in the data set. There are lots of false ones, so even applying some scrutiny, some screening, some methods, et cetera, you only improve that much on the first go-around. And it has to be a more iterative process instead, where you go through and say, okay, we've improved the data set a little bit, but let's go back and do another kind of layer of scrutiny, and another and another. This is why in many medical fields, women, for example, if they're diagnosed with breast cancer, will have 2 or 3 positive tests before it becomes actually more likely than not that they actually have breast cancer if they're a young woman, for example. And so kind of being very rigorous and understanding that it takes a long time to kind of find those proverbial needles in the haystack is an important part of data science today. The third, and again kind of related problem, is that we are also in a competitive environment, that we are trying to discover things that our competitors have not discovered, or things that are being done wrong by other people in the market. So there's always a question of what happens where we encounter a positive finding. Is that a feature, something we believe that we have discovered uniquely, or is it something that is just like a bad line of code or something? But so I live, as I mentioned, in Manhattan. I was giving a talk a couple of years ago at the Guggenheim, which is on 89th Street and 5th Avenue. So Manhattan, the traffic is really bad in Manhattan, but we don't have any of the weird like diagonal streets that you guys have here. It's all just a grid. And so getting from point A to point B is, as a navigational problem, supposedly very simple. So here's a simple route you could take that Google Maps would recommend, going from my apartment to the Guggenheim. By contrast, the route that my driver took that day was the following route instead. So we crossed through Central Park 3 times, did like a loop-de-loop at 68th Street, it looks like, and then finally got there about half an hour late. So the question is, why was this guy taking this route? And the answer is that he was following the GPS directions turn by turn. This is what the GPS application that he had, I'm not sure which one it was pre-Waze, so something more primitive probably, but the GPS step by step. And what the GPS correctly determined is that there was a route that cut north to south through Central Park called East Drive, and that there was no traffic on East Drive. So it was saying to the driver, just get on East Drive, it's a shortcut. Once you get on East Drive, then you're home free. You can literally be there in like 2 minutes. The problem is that East Drive is only open during rush hour. This was 2 p.m., not during rush hour. His software was not instructed to know that. And so, in essence, he was saying, okay, every person in New York, all other 8 million people, are idiots for not knowing about East Drive being this like shortcut, basically. And so it was desperately trying to turn on East Drive before he finally realized that like you should probably not cross Central Park 3 times on the same journey unless you see like Godzilla on the Chrysler Building or something. But there are lessons here, one of which I think has to do with the fact that, again, we are in an environment where we are in a competitive landscape, where there is a market consensus, or there is feedback from a community, and so it's a higher threshold to be right when you're also implying that everyone else is wrong. Also, though, I think the matter of like, when do you trust the algorithm versus your experience or your gut instinct? I've, since this occurred, kind of paid a lot of attention to what happens when the GPS recommends, either because you're driving or your driver is or whatever else, has something screwy that it recommends. It's kind of 50-50, actually. There are lots of times where that instruction actually doesn't really make any sense at all, and it kind of can lead you to like a deserted highway somewhere in the middle of Kansas City or something. Not speaking from experience or anything like that, but you have to be careful. But the role of gut instinct versus more algorithmic or systematic thinking, I think what most lay people do out in the real world is they will lead with their gut. So they'll say, okay, I have an intuition about how the system works. I'm going to apply that intuition, and then at the end, I will do some data science, the last 20% to kind of prove that intuition, right? I think that's like the reverse of the process that you should apply. I think the process should instead be that you start out, get 80% of the way there, with trying to be as rigorous and as disciplined and as kind of regimented about your thinking as possible. And then the 20% is where you apply your experience and your creativity to kind of solve the last mile problem, so to speak. So a case like this, where the GPS is recommending something really unusual, that's where the driver's experience probably ought to come in, and he should say, this doesn't really make any sense at all whatsoever. Probably over the long run, yeah, the GPS will be better than his gut instinct for which navigational directions to follow. But when you're in those edge cases, avoiding false positives is something where experience can be extremely useful. And even the instinct to have a sense for, hey, here's where a solution looks a little bit funny, where it's too good to be true. I think that is important, and why we do need kind of human capital in this industry. It's not all a matter of just kind of automating everything. So moving on, I want to talk more about kind of what I think of as just best mental practices when dealing in the era of big data. And these all stem in one way or another from Bayes' theorem. Bayes' theorem you're probably familiar with. It's a very kind of old and very simple algebraic formula, which is just all about how you incorporate new information when you already have some pre-existing belief about the world. So in Bayes' theorem, of course, you start out with what's called a prior belief or a prior probability. In fact, it is important that it is a probability. You can't just say, oh, I kind of feel this way. You actually have to be explicit about saying, here's where I think the chances are to start out with. And then you update that as you collect new information. So there are kind of three basic principles that derive from this. Number one, think probabilistically. Number two, know where you're coming from, meaning you start out with a prior. And number three, try and error. So I'll explain each one of these in a little bit more detail here. One of the big challenges that we face at 538 is communicating, particularly around politics. It's actually a little bit easier around sports. People have an intuition in sports that that a team, for example, can go 0 for 27 on three-pointers. That will be an unlikely event, for example. Good for you guys, though. But in politics, it's hard to communicate the idea that there's an element of uncertainty. You can call it randomness or not. It doesn't have to be like metaphysical randomness, but communicating uncertainty is a big challenge in a field where people want definitive results all the time and feel a lot of sense of righteousness from when elections turn out a certain way. But it's not limited to politics. You know, for example, weather forecasting is a field where there is a lot of challenges of communication too. This example comes from a problem the Weather Service encountered in 1997 when they were trying to forecast flooding in North Dakota. So North Dakota, obviously pretty cold up there. You get a lot of snow every winter. And so if you have that snow, if there's too much snow, if it melts too fast in the spring, then you can have the risk of flooding in rivers up there. So one year in 97, you'd had a really, really heavy snowfall, melting quite fast. And the Weather Service predicted that along the riverbanks in Grand Forks, North Dakota, you would have the floodwaters crest at 49 feet on the peak of the flood in March. People there, it's a pretty well-educated state. They were like, you know what, we have flood walls that go up to 51 feet. 51 is more than 49, so we're going to be safe, right? Well, maybe not. What the Weather Service, forgot to tell people was what the margin of error on the forecast was, which is plus or minus 9 feet instead. So in fact, it implied there was a 35 or a 40% chance of a flood. They had been afraid, it came out later on, that if they conveyed uncertainty in the forecast, they thought people would not trust the forecast at all, and so instead left people totally unprepared. A lot of times, this is a canonical example, but a lot of times the uncertainty is the most important part of the forecast. And getting kind of the point estimate right is relatively easy, but understanding is a margin of error 9 feet or 2 feet or 20 feet, and how much that matters for the way you communicate the information to the public. That's where the challenge comes in an awful lot of the time. I don't mean to pick too much on weather forecasters. In fact, if you read my book, they're kind of some of the heroes of the book. They've gotten very good at what they do, and they've also gotten very good at trying to communicate probability visually, for example, in hurricane forecasts where you see, this is the hurricane forecast for Irma late last year, where you see the different paths that the hurricane takes, and it kind of goes from having a forecast track on the west coast of Florida to the east coast, but always within this cone of uncertainty, as they call it. People don't always pay attention to that. I remember reading about Hurricane Irma, and at one point the AP said that, well, there's been a big change in the forecast. Now it'll hit Tampa Bay instead of St. Petersburg. If you know the geography of Florida, they're like sister cities, and so like that way overestimated the precision of how good a hurricane forecast is. But still, it's a case where forecasting has improved a lot over time. So it used to be if you had a hurricane sitting in the Gulf of Mexico 3 days or so in advance of landfall, the average error, this is not just a margin of error, the average error would be a 350-mile radius on average. So completely useless forecast to say the hurricane could hit anywhere in Mexico, Florida, Texas, or maybe loop on up to North Carolina, right? Not very helpful at all. Now, you have accuracy within about 100 miles on average instead, several days in advance. 100 miles is still enough where you're covering the entire Florida peninsula, which is skinny, so not perfectly precise, but you can plan evacuations, save a lot of lives. We have had, obviously, some bad hurricanes in the past decade in the United States. We have a lot less loss of life than we used to because hurricane forecasting has gotten so much better and given people more advance notice. So why has weather forecasting improved so much? Again, if you read the book, you'll find that there are lots of fields where there hasn't been very much progress in forecasting or predictability. It's really based on a combination of three things. So number one, weather forecasting, we understand the chemistry and the physics of the atmosphere really well. In other words, it's not like a naive kind of machine learning black box approach. It's kind of very directed and hypothesis driven and is saying we understand the equations, we just need different ways to solve them. Number two, there is a computing component to this, where weather forecasting works by like separating the atmosphere into tiny little grids or pixels. So for example, you can imagine that, hey, so 100 years ago at the dawn of weather forecasting, New York and Boston were like in the same grid and would get the same weather forecast. You can imagine out here, for example, where I've been out here enough to know that like it can be like a totally different climate in Oakland than in San Francisco. So the more you can refine that grid, the more accurate and precise your forecast can be, but it's also very computationally intensive to be basically modeling the whole atmosphere in real time. So computing power is important. But third, and maybe most importantly, is weather forecasters have a lot of practice every day at what they do. Where weather forecasters make forecasts, I think, in roughly 420 cities around the United States every day, 24 hours a day for 13 different variables of interest. So you can be pretty bad at forecasting at first, but if you get very constant feedback and can make corrections and amend your algorithms, then you can be very good over the long run. And so the combination of kind of theory, practice, and technology, those three things together, can make people very powerful at forecasting. Idea number two, so know where you're coming from. So under Bayes' theorem, you always start out with what's called a prior probability or a prior belief. And how you determine that prior is an interesting question, but it has to do with your experience, you can call it your biases or your prejudices or whatever else. But the point is that people talk about, oh, how can I be like more objective? I mean, the problem is that by definition, any one person is inherently subjective. It's like literally how the term is defined is like, I am a subjective person. I am trying to, however, understand what the objective world is like. And so the question is, when do people who are working in groups or teams collectively come to a better and more accurate understanding of what the real world is like? Or when do we kind of feed off on one another's mistakes and wind up in an environment where there's a lot of groupthink instead? So one book I'd highly recommend, if you haven't read it, is James Surowiecki's The Wisdom of Crowds. He's a writer for The New Yorker and talks about when kind of group wisdom fails or succeeds, and he finds there are three basic types of qualities that are important when working with data. Number one is that you want teams or groups that are diverse. So diversity can include things like racial and gender diversity, but he's mainly referring to diversity of thought and diversity of skill sets, which can be correlated, by the way, with racial and gender diversity. But meaning that if you have 100 people who are really smart in the same room, but they're all smart in the same ways, what's the phrase? I'm going to mangle this probably, but you can't create a baby in 1 month by getting 9 women pregnant, right? It's kind of the same thing. If you have 100 people in a room together who are all skilled in the same ways, you encounter redundancy really fast. And so when you're building teams of data scientists having different skills, this is one thing I've learned at 538, right? Where I'm someone where I'm a little bit of a jack of all trades, where I can do some writing, I can do some data science work myself, right? Can go out and try and promote 538. You're better off finding different components that work together as teams and can play off one another's strengths and weaknesses pretty well. Number two is independence. So the idea of a crowd being wise is that you bring people together who are able to articulate and express their views and have debates and disagreements. So cultures that foster people that kind of question results when there are things to debate is very important. I'm reading the book now about called Bad Blood about Theranos, and about kind of how long these practices were able to go on for years and years and years based on an environment that suppresses dissent. The minute someone would question Elizabeth Holmes, she would fire someone, kick the door out on the way out, and make sure that there was no opportunity to really have dissent within the company. So being able to have disagreements, being able to, without fear of reprisal, being able to question your boss, being able to tell your employee when she or he did a bad job with a project. Collegiality is important, but that's really important as well. And the last kind of plank of what he's found is helpful in these environments is having decentralized processes, so we can actually be in an environment where we collect data independently, where you have a local view of what conditions look like on the ground. That can be really important. You're actually bringing more information to the table potentially. Where you're more, again, it's kind of all about like the edge cases where the algorithm says one thing and maybe people on the ground say another, being able to actually dig in and examine those and say, hey, look, our algorithm, our model is pretty good, but there is important information that it's not accounting for, and maybe based on that reporting we see people on the ground, we can think about, are there things systematically that we're missing in our model or in our system? So these three characteristics can determine whether getting groups of people together can actually make for better data science, or instead can lead to huge amounts of groupthink and lots of problems. The last thing that's important under Bayes' theorem is simply the importance of trial and error. I talked about that a little bit in the weather forecasting example, but let me give you another example from the realm of poker. So after this trip, I'm actually going to go out and play a little bit of poker in Las Vegas, which I'm really excited to do. For a couple of years in the mid-aughts, I actually made my income for the most part as a professional poker player. And there was kind of a poker boom at the time, it was called. I think it's really more of a poker bubble, frankly. But it was caused in part by this guy here who is named Chris Moneymaker. And so Chris Moneymaker was an accountant, worked for Deloitte & Touche in Nashville, Tennessee. He at one point entered a qualifying term, I think deposited $70 at PokerStars, try and gain an entry into the real World Series of Poker in Las Vegas, Nevada. Won that qualifying tournament. He actually was trying apparently to lose the tournament. It just came out recently. He didn't want to actually have to go through the hassle of just going to Nevada. He wanted to actually just get $8,000, which was the second prize, but instead he got an entry, $10,000 entry into the real World Series of Poker in Las Vegas, Nevada, and won that tournament too. So it took $50 or $70 and turned that into a $2.5 million first place prize. So it wasn't quite, it's not quite rags to riches because he's like already like an upper middle class consultant. But you know, for poker standards, a guy named Moneymaker winning, defeating all these pros was a very good kind of made for TV story. But when you see poker on TV, you see it like this, where this is a famous hand where Chris Moneymaker misses his draw. Sam Farha, this old kind of grizzled pro who is like chain smoking, has top pair, and Moneymaker goes all in as a bluff, and Sam Farha folds. So if you're watching this game on TV, you're like, you know what? I'm a lot better than Sam Farha, right? I would not have folded. I would have known that Chris Moneymaker was bluffing, which you would have if you had X-ray vision like you have on TV and can see Chris Moneymaker's cards. And so poker is edited for TV where you kind of are able to have total knowledge of what hand your opponent is playing, and they kind of edit out all the boring hands where Chris Moneymaker plays poorly. So people would watch poker on TV and get a false impression of how easy it was to beat poker. In fact, poker is a game that requires like a lot of luck but a lot of experience over the long run. Poker was interesting though because, you know, as a poker player, I was like in some ways fairly data driven. I collected a lot of data on how my opponents were playing, and you can kind of stylize that data. So this, for example, is an estimate I developed of how much each player is making or losing over the long run at a typical 9-person or 10-person online poker table. Mid-stakes, no limit hold'em. So one thing you see here is that, number one, the average player loses money by definition because the house takes a cut, but also it's like way easier to be really bad at something than really good at something. Where the worst part of the table is losing $420 or so per hour. If he just folded every hand instead, he would only lose $200 an hour instead through the blinds. So by trying, he's making things twice as bad. The best player commercially is making about $100 an hour instead, which is a nice profit, but still, there is in some ways more downside than upside here. But poker is a game which in some ways is a game of information, a game of data science, and you kind of see the learning curve here that you can generalize from that pattern. Where, so the 80-20 curve kind of comes from sales and marketing, where it says 80% of your sales come from 20% of your customers. You know, we're often in a world now where it's a 95-5 world instead, not just 80-20. But this principle is also important, I think, in the realm of data science, where you want to think about which part of this learning curve am I on. There is at first this kind of nice, kind of steep part of the learning curve where you're making a lot of improvements very fast. So if you do sit down and begin to play poker, you'll be really awful at first. But if you just take a fairly basic approach, where if I go from a strategy of playing like a total donkey to instead saying, I'm going to fold my bad hands, I'm going to raise with my great hands, and call with my mediocre hands, right? Like that's the right strategy 80% of the time. There's no bluffing into that strategy, so you won't make money in the long term, but you go from losing a lot to losing a little bit. If you guys are familiar with the story of Billy Beane and the Oakland A's, which you might be out here, and Moneyball, that was a case also where there was low-hanging fruit in the baseball industry, where Billy Beane realized that, hey, teams are undervaluing on base percentage, took over as GM of the A's, and began to acquire all these players very cheaply with high on base percentages. People don't tell the aftermath to Moneyball story as much, though, where the whole league realized, hey, Billy Beane is right. OBP is now undervalued, and so now we're going to also acquire players that have high on-base percentages, and the A's advantage dissipate. They kind of reverted the mean of playing in this really crappy stadium in Oakland. Once the market realized that, hey, Billy Beane actually was correct, but your edge oftentimes in the industry only will persist for 6 months, a year, or 2 years before the competition will catch up potentially. So oftentimes instead we're at this other part of the curve where the learning is more incremental and we make improvements 1% or 0.01% at a time. The point is simply that when you are in a competitive environment, as the kind of water level increases and everyone is doing the easy stuff, then you gain your competitive advantage through relatively marginal and incremental gain. So that's meant to be encouraging. I meant to say that, like, if you look at companies out here in the Bay Area, Silicon Valley, that are successful, they all take a super incremental approach. I mean, Google or Facebook or Uber, there are lots of things you can criticize with them, but one thing I think they do well is they say, we're not hung up on having any one particular golden algorithm. We're going to constantly kind of tweak and revise things, and we are definitely going to like screw things up a fair amount of the time. But the process of like actually learning from experience, learning from customer data, understanding that you can model something in the abstract, and generally speaking, I think having like having one nugget of like actual information is worth kind of 10 pieces of theoretical or kind of back-tested information. So improving at the margin and making gains that way instead of iterating over time. If someone comes to me and they say, hey, Nate, I have an algorithm that can kind of make your presidential forecast 50% better, I'm like, it's probably BS, right? If it's 5% better or 0.5% better, that might be a realistic improvement instead. So I'll go to questions, but I want to leave you with this thought, which is actually like a little poem from Piet Hein, who's a Danish scientist and author. The Road to Wisdom. Well, it's plain and simple to express error and error and error again, but less and less and less. So thank you very much.
Hey, Nate, thanks for the talk. Great stuff. Have there been any studies that you know of that try to quantify the amount of information that can be extracted from a data set so that you know when you're at your limit?
Not that I know of, but that's a really interesting concept, right? There's only so much kind of juice you can squeeze out of a particular lemon, and I think there are some techniques that are just like, so basically like there's a limitation on how complex your technique can be based on the amount of information the data set contains, but no, there's no, I mean, maybe there is, but I'm not aware of it. But yeah, having like a measure of like maximum possible amount of information would be, I think, a useful indication.
Hi, Nate. Thank you so much for the talk. I just finished your book, really enjoyed it. One of the new ideas that I encountered was when you talked to Philip Tetlock, and he sort of explained the whole difference between hedgehog thinkers who know one very big thing and then fox thinkers who know many little things, and that foxes are sort of better predictors. And so I guess what I wanted to ask was if you've ever had any success in sort of teaching a hedgehog to be more fox-like, or teaching perhaps like an enterprise that's like has a lot of hedgehog thinking in it to be more fox-like, to maybe like talk people down from their unjustified level of certainty.
Yeah, so Phil Tetlock has written books that are like, he's done like 30-year studies of forecasting and like what characteristics of people actually make for better forecasting. And he's found that characteristics that are more fox-like. So it's a little tricky to define, but like it comes from the quote that the hedgehog knows one big thing and the fox knows many little things. So people who are willing to be incremental, people who are not too ideologically driven, people who are willing to change their approach quickly, kind of keep their head down kind of thing. What might happen here in like a Silicon Valley type of environment is that very often like founders are very hedgehog-like, right? They have like one big idea, and they want to see that through, and they believe very much in that idea, and that can be helpful for some things like increasing the amount of optimism in the business. But most data scientists are successful by being more fox-like and more incremental. I mean, how do you train that? I mean, I don't know. I think it's partly just a matter of getting your feet wet and having a lot of experience. It's partly a matter of having like good communication within your industry or within your company. I mean, the thing is like, the data science cannot overcome cultural problems at a company. We saw this in baseball a little bit. We're back in the kind of Billy Beane's still managing the A's, but back in the kind of Moneyball era, 2003, teams would start to hire people like me, they would hire stat heads, but then kind of like lock them in like broom closets and not let them really like be influential in decision making throughout the team. And so like making sure that like people who are not practitioners of data science actually understand what the data science is to the extent possible. People understand that, making sure that also people who are data scientists understand the company's mission and goals. I mean, that still is extremely important, I think.
The effort to accuracy chart, the diminishing returns, your slide next to last.
Yeah.
How do you think this interacts with the winner-takes-all nature of today's competitive markets?
Yeah, no, it's true, because I guess that formulation is kind of in an environment where there are potentially many spoils to be had that can be shared between different companies. You know, obviously there are fields now, you know, I'm reading various books on artificial intelligence. That's a field where, you know, AI, because of the kind of notion of where you maybe have exponential returns to that, it could be a case where whoever gets there first is a lot better. And so, yeah, I think that introduces more chaos into the system, frankly, where having one edge and being kind of in the right place at the right time can lead to disproportionate gains. And that would affect the calculation somewhat. It might mean that you actually want to spend, I think, more time in that first 20% where you're taking moonshots, I suppose, or trying like fairly random ideas because you hit on one and you have all of a sudden you kind of win the game, right? Versus a case where gains are more evenly distributed between different competitors in an industry.
Yeah, Nate, thanks for the talk. Would love to hear you talk about how you see your duty as a data scientist, particularly in the current political environment, and because I see from the kind of likelihood of a Trump victory that you predicted that was much higher than, say, Daily Kos. Some of those organizations would, I think, probably advocate for being more partisan or trying to influence public opinion in a certain direction. Do you see yourself as doing a duty to simply convey the current state of things and the best likelihoods possible? Or do you feel there's a point at which you would become more partisan and look to influence public opinion?
No, look, it's a pretty clear duty when you're a journalist that you're just trying to convey information as accurately as possible. You know, understanding that people may not interpret information the way that you intend it to be heard, that some people will see a 70-30 forecast and they'll think 70-30 means Clinton's going to win for sure, right? And so understanding that like kind of communication can be a challenge. But definitely, my goal is to convey information as accurately as I can, even if it means that people don't like it. This gets into questions of like journalistic ethics, but in general, I don't like when journalists suppress information. If there's a name, for example, of a school shooter, some people say, well, you shouldn't kind of publish that shooter's name because then that will give more publicity to the shooter. It might be true, but the goal of journalism is to provide accurate information to people. And it's kind of, once you begin to cross that line and say, okay, when is this going to influence things in a certain way, it's hard to kind of uncross that line, I think, and it's hard not to become a partisan after a certain length of time. So I think just saying, look, my goal is to provide information, do the best job I can, making sure the information is accurate is a pretty clear line in the sand for what we do at 538.
This is kind of related to the last question, but what have you learned at 538 about making data-driven writing interesting to a broader audience?
It's a great question. Maybe the first thing that comes to mind is just that it takes a lot of time. To really kind of communicate data-driven writing, then you probably have to have different ways in for different people, where some people are going to learn through the actual numbers themselves. Some people will learn through being able to download a data set. A lot of people will learn through charts. A lot of people will learn through careful writing or through narrative or through storytelling. And so making sure that like you're able to appeal to readers who have varying degrees of sophistication, and just taking a lot of time with editing stories, making sure that the presentation is visually attractive is really important. Making sure that, editing also means editing down, so removing parts of the problem that are inessential. If I sometimes read data science type 538 articles from amateurs, then there's just too much there, right? It's too much for the reader to sort through, and it's like part of your job as a writer or an editor is to say, here are the parts that are essential, here are the parts that are important context, and then here are the parts that you don't have to know about for right now. Maybe here's a data set or a series of footnotes where you can go into more detail if you want. But yeah, the importance of editing and data visualization is kind of the key. It's hard to do that off the cuff. It takes more time to write a 538 type article that's going to be effective and have a big audience than it would for a more traditional work of journalism, I would think.
Given the explosion in the universe of data, the rate at which things are changing in our in our landscape, the difficulty in harvesting that data, wrangling that data, what does the future of the way data scientists work look like? Does it look fundamentally different? How do we deal with everything needing to be faster, given that the work we do is not always fast?
I mean, maybe it's a little bit self-absorbed. I hope the world will accommodate to data scientists' needs and not the other way around. And I kind of hope that that people understand that there is a trade-off to speed. I mean, that's also related to the last question too. Where if you want to do something in a day, which you sometimes have to do in like a news cycle environment, it's not going to be as good as when you have to do things in a week or a month. A lot of stuff that we publish at 538 is stuff also that you could publish in an academic journal. It would take a year to come out, and we'll publish the article in a week instead. So it's kind of like figuring out when you can do something fast without having potentially fatal trade-offs, right? Like, when is that 80% approximation good enough or not going to get you in very much trouble? When is that potentially, though, going to cause a huge crisis? If that 20% is a case where the whole kind of system can blow up, then it's a very different environment than when you kind of get one thing that's a little bit off in one direction or another. So thinking about time management issues, I think, is pretty important. Okay, thank you guys very much. It was great to talk to you today, and have a great rest of the conference.